So thank you very much to Sugato for giving such a nice preface or forward to what I'm going to talk about. That would be the third experiment I'm going to talk about, but I actually wanted to talk about three experiments we are working on, and they're all in the interface of general relativity and quantum mechanics. I apologize, but I'm still here with the old-fashioned acknowledgement. But once you send that sentence, I'll be happy to acknowledge all the foundations. And also, credit is due to Igor Pikovsky, who is here for this beautiful picture, which I like to use. So I want to show you quite a bit of stuff, so I'm going to a little bit rush through the slides. I apologize for that. And I hope you drank a lot of coffee so that you can actually follow. Okay. All right, so the outline is very simple. The motivation, well, that's clear. Two techniques that we use in all three experiments are Stern-Gerlach interferometry and atom chips. And then I'm going to speak about the three experiments: clock interferometry, the quantum equivalence principle, and nano-diamond interferometry, which connects to what Sugato just said. And actually, Shimon has already talked about clock interferometry and quantum equivalence principles. So thank you also for that introduction into the subject. Okay, so you have a camel on the top right, and that's the most common animal around our lab, and they always seem to me very, very curious animals. So we try to just imitate them and be very curious. Okay. So motivation is clear. Modern physics stands on two pillars, and actually that's very disturbing that we have not been able to put them together. And some people hypothesize that the lack of unification actually hints at the fact that at least one of them has something fundamentally wrong with it. That's, for example, the point of view of Roger Penrose. So that motivates work at that interface. Okay, so the two tools we're mainly going to use is the atom chip, this mature technology that started now 25 years ago. And what you see here is the artist view. You have atoms a few microns above the surface, and you have electrodes manipulating these atoms, doing magnetic gradients, electric fields, light fields, whatever you need. This article is from Jakob Reichel. It's from the group of Ted Hensch, who was one of the three groups that started the business of the atom chips. At the time, I was with Anton Zeilinger and Jörg Schmidmeier at Innsbruck, and the third group was at Harvard. Here you see from our lab how it looks like in reality, and you have the atoms very close to the surface, and this is an image from the surface. That second cloud is just a reflection. And the technology is mature enough to go to space, so already 3 atom chips made it into space, and the first one with the German Space Agency. One is now operating continuously on the International Space Station, and I heard that one has just been sent onto the Chinese space station. Okay, it gives a lot of advantages, this atom chip, but the main one, I'll just focus on one, is the magnetic gradient we're going to need for the Stern-Gerlach interferometer. And so you could get from these wires very strong magnetic gradients. I give here an example. If you just run 10 amp and your particle is 1 micron away from this very small wire, you can get 10 to the 6 Tesla per meter. You cannot get that from coils. And there is no inductance, so the switching on-off is very quick. All right, Stern-Gerlach, you all know about it, 100 years old. I won't say much about it, except to say that this is now a historical physical site. The building is still standing in Frankfurt. It's really nice to visit it. And in 2019, we actually inaugurated it as a historical site. And here you see Stern-Gerlach. In the middle, it's Lisa Meitner, who worked with Otto Hahn. I always like to say that she was nominated 48 times for the Nobel. She never received it. And there are all kinds of historians debating why. Okay, so if you want to know more about the Stern-Gerlach program that we have, you could go to this very nice article from Quantum magazine. which describes it and also describes the work we did so far and our plans for the future. So how does it look like in space-time? So the x-axis is time, and the purple areas are the magnetic gradients from the atom chip. And the light blue areas are just internal manipulation, the manipulation of the internal spin. So pi half pulses put this spin 2 into a superposition of 1 and 2. You could just treat it as up and down in the Stern-Gerlach experiment. And then this we call the half loop, because we have here 2 wave packets, and we let them expand just like in the double slit experiment, and you get this spatial interference pattern. This we call the half loop. But what is more interesting for us is the full loop, which is really harder to do, and you have 4 of these magnetic gradients, splitting, stopping, accelerating back, and stopping again the relative motion, and you get these oscillations of spin. Okay, so you have one signal, it's spatial interference pattern, and spin oscillations is the other observable we're working with. So this is an artist's view of how it looks like. So you have the atom chip. You start with a BC below it, but it's single atom physics. It's a very dilute BC. And then you do this spin up plus spin down. You do a magnetic gradient from the wires, and you get this 2 wave packets, and then they overlap, and you get this interference pattern. So now we are, there's over a decade of experiments. Again, this is the spatial interference pattern. This is how these spin oscillations look like. These are 2 observables. And after a decade of Stern-Gerlach interferometry, it looks like this is becoming really mature, and we understand this kind of experiments. So the first experiment I want to talk about is clock interferometry. Shimon has already talked quite a bit about it, so I won't say much. This is the paper that motivated us from the Bruckner group, and you see here Magdalena and also Igor Pikovsky is on that paper. And these are papers that we published about it, and all I want to add actually is that there's a paper that people have not are not still aware of. It just came out recently. And this brings into the game another tool, I would say, and that is geometric phase. We call it geometric phase amplification. And I think this new tool could help quite a bit fundamental experiments like the ones Shimon wants to do, and metrology. And so I think this addition to clock interferometry of geometric phase is really interesting new game that we need to play. And just so you see how far it may go, just in an anecdote, I show you a letter, an email I got just a couple of days ago from a scientist in the US. After many kind words that he says about this paper, he actually says that he thinks it's even connected to, one can think about its connection to biological systems. So this could go in the future into many different directions, and that's the beauty about that's the beauty of science. All right, so I will not spend time about clock interferometry, and just to show you that this graph actually shows that time is a which path witness, because this is interference visibility, and this is the synthetic. We didn't have clocks that are good enough to measure the real redshift of Earth, so this is synthetic redshift that we applied, and you see how the visibility oscillates just as predicted by the theory paper of the Bruckner group, and that was really the first observation that time is a which path witness. And here you really see these 2 Bloch vectors are the two clocks, and if you paint the right picture with them, you get the geometric phase that I just mentioned. We're now building a ytterbium clock, by the way, to repeat these experiments with a much better clock that is sensitive enough to feel the redshift of Earth. Okay, so let me jump forward. The second experiment I want to describe is a recent experiment we did still with the rubidium atom. And I mentioned here the mass, 10 to the minus 25 kilogram, because in the next experiment, we're going to jump by 10 orders of magnitude to nano-diamond, which is 10 to the minus 15 kilogram. So it's quite a jump. So we set out, actually, to measure this phase. And the first author here, by the way, I should mention, Ordopkovsky, is sitting right there. If you want to ask him questions, he just raised his hand. He did marvelous work. So he led the experimental team, and there are also many theoreticians that you can find here in the author list. So let me explain to you what is this phase that we wanted to measure. You know what M and G are. H bar you know. So T is the interferometer time. And this is just a phase that is accumulated as the interferometer time to the power of 3. Okay? And that's quite a unique phase. And so this picture from a paper by Roger Penrose and colleagues was talking about, let's say that we have here an object, and we split it into 2 wave packets, and one of them goes into free fall. The other one is static on the table. What will be the phase difference between them? And in principle, if you just say that the static wave packet has 0 phase except for free evolution and so on, then you're just asking really what is the phase of a freely falling, the quantum phase of a freely falling object. That's the question that Roger Penrose and many other people have posed. Actually, people have started to talk about the phase of a freely falling object 100 years ago already. Yeah, very soon after quantum mechanics was born, people started to ask this question. The problem is here for experimentalists is that this guy is going away very fast from the other wave packet. You have to close the loop in space-time in order to see the relative phase. That's the problem for experimentalists. And this is what we came up with. So what you see here is height. Yeah, above Earth, if you like, or distance from our atom chip. Here are the wires that create the magnetic gradient. And with these magnetic gradients, we can actually form here a beam splitter, where one wave packet is going into a ballistic flight, so it's in free fall. And the other one, that's the one on the table that I just showed you, is fixed in a potential relative to the atom chip or relative to Earth. And so what happens here, that this is a hybrid interferometer. Typical interferometers you find on Earth are either all the time in free fall, free space interferometers, or they are guided, or they're both wave packets are in some potential. But here we had to form a hybrid interferometer where one is completely free of any potential except gravity, and the other one is in a magnetic potential formed by these wires so that it's static relative to Earth. All right, so this is what we decided to do. And in the lab, really, it starts here. We split this atom, this rubidium atom, into 2 wave packets. One is catapulted up and down, and the other one stays static. The actual experiment is quite complicated, and I won't go through the different stages. And here's the atom chip that was used for this experiment. And so this is the data. And from this data, we extract the result. And when you look at the result, which is the phase as a function of time, you find that it fits exactly to this term that I told you about before. And we did the numerics, we did the analytical, and it really all fits very nicely. OK, so we have confirmed the phase of a freely falling wave packet. But what is the connection to quantum equivalence principle? What is the connection to the equivalence principle? Well, people have started to talk about the connection to the equivalence principle in the quantum domain quite a while back. The first paper I could find is this paper here from '79. First author is Daniel Greenberger, the same G from the GHZ state. He actually lives and works here in New York. For those interested in an interesting discussion, I just met him recently in Vienna, and here they're celebrating his 90th birthday in Vienna. But this paper was followed by many other papers talking about how to measure the equivalence principle in the quantum domain and the connection to the phase of a freely falling object. So I don't have time to go through the whole thing, but just very briefly, Einstein said that something in free fall does not feel weight. And that is because that in the free falling frame, yeah, if mi, the inertial mass times acceleration a, is equal to mgg, that's the equivalence principle, then there should, in that frame, should not feel any weight, and there are no forces in that frame. So this, if you look at the ballistic wave packet in a freely falling frame, then it's like this, experiment happening, or the wave packet is in this spaceship that is accelerating with g relative to Earth. And then if this is correct, there are no gravitational forces, so the phase due to gravity has to be 0. And then through Galilean transformations, we know what the transformation between the freely falling frame to the lab frame where we do the measurement is. And from that, we can extract the phase that we should measure in the lab. And it's exactly no surprises there, it's exactly the phase of a freely falling object. So if we would have measured another phase, it would mean that the Einstein equivalence principle cannot be applied to the quantum domain. But we did measure that phase, and that means that they are compatible. They coexist nicely, at least in these low energy regime. Okay, the last experiment, I'm already in yellow, so I'll accelerate. So the last experiment was already motivated by Sugato, and there were numerous papers starting from 2013, this paper here. Gavin is, of course, also here in the crowd. And the idea was to take this Stern-Gerlach and apply it to the spin here, single spin in the middle of a nano-diamond. And so since we are we're very happy with Stern-Gerlach interferometry, we decided, let's do that. And so this has already been shown, Anupam and Sugato, but I just wanted to mention that long before we do these two interferometers in the entanglement experiment, this kind of single interferometer is already going to be able to test a lot of interesting stuff. Quantum mechanical superposition in new regimes, continuous spontaneous localization model, testing exotic things like the fifth force or the Diossi-Penrose collapse. There's a lot of models out there, exotic models out there that one could test already with a single interferometer. So you need a lot of work in the lab to get this going. And here I actually put a list of 8 building blocks that you need to achieve if you want to do this experiment. And you have to have very accurate nanodiamonds. So we are fabricating these nanodiamonds ourselves. You need to do UHV loading. You see here nanodiamonds being loaded into a trap. You need to cool. So here you see temperature going down. You need to have very strong rotation cooling. Here you see a very asymmetric, you see a nanodiamond here in a very high frequency trap, which is also asymmetric, which is very good for rotation cooling. You need to neutralize them against decoherence. You need to do NV spin manipulation, which is what you see here, Ramsey fringes, and neutralization you see here. And you need the Stern-Gerlach interferometry. This is the graph I showed you before. And our chair is already standing. So let me just very briefly say a few interesting words. First of all, this community, as Gavin is going to show, is growing continuously. That's beautiful to see. More and more groups are coming in. Just yesterday, I got this email from China that this is a new group that wants to do the experiment, and they're asking for advice. So this is really nice to see that more and more groups are coming in. But there are theoretical barriers. The first very interesting theoretical barrier is as your object becomes large, you don't have to only care about or worry about the external environment decoherence. You start having an internal classical environment inside your object. So Carsten Henkel has actually calculated that from a certain object size, our coherence is going to be killed not by the external environment, which is like black body radiation and so on, but the internal environment is going to prohibit us from making large object superposition. I really advise to read that from last year, to read that paper. I think it's an inherent limit in quantum mechanics. There is the Humpty Dumpty effect, the problem of closing the loop in space-time. This came from these 3 gentlemen in the 80s, a series of 3 papers. This is Marlon Scully, who taught me all about the Humpty Dumpty effect. But typically, people think that it's only about delta P and delta Z at the end. These are experimental imprecisions in closing the loop in space-time. It's much more subtle than that. and we started to calculate the Humpty Dumpty effect due to rotation. This is a paper from 2 years ago where we started to work on this rotation, and you see here contrast falling as a function of the interferometer time, but also of the rotation speed, the angular speed, and that's a very big problem. To close it in P and X is relatively easy, relative to the problem of Humpty Dumpty due to rotation. So rotation actually introduces orthogonality, which path information, which kills your ability to see any contrast. Okay, conclude. I'm going to conclude, and our chair is happy. So, following the failure of theoretical efforts to unify quantum mechanics and GR, experiments at the interface need to start giving hints. And more experimentalists are going into this topic. Working at this interface may reveal new things about both theories. I presented 3 experiments at this interface. We're working on all 3 of them. And the emphasis now is on a nano-diamond. So this is the new effort we're building, jumping from the rubidium 10 to the minus 25 kilogram to 10 to the minus 15 kilogram is not a simple jump in the lab. And I present progress in the 8 required building blocks. And I have to thank the people doing the work. So here at the center, again, is Or Dubkovsky, who has his hands in all of these experiments. And some of the people already left us. And many theoreticians that are helping us understand these very complex systems. And thank you for your attention.